We're starting section 3.1, the definition of derivative. We're finally there, and we're going to cover 1, tangent line and tangent slopes, 2, instantaneous rate of change, 3, differentiability, graphical and algebraic approach. So far we've talked about slope of secant line a bunch. What is slope of secant line? Is just the change in y value between 2 points on the graph, and divided by the change in x value of those 2 points. Now, if you keep one point fixed and then bring the other point closer and closer to that point, infinitesimally close, then you end up with a tangent line. And so basically, now that we have the words, we kind of went around this a little bit when we were starting section 2, and so now it's officially slope of tangent line as the limit as x approaches a of f of x minus f of a over x minus a. It's basically the limit of the average rate of change as one point approaches the other. And so the approaching can be from the left side or from the right side, either side, as long as the other point is approaching this one point. Now, derivative of a function at a point, the derivative of a function y equal to f of x at x equal to a is f prime of a equal to that limit as x approaches a of f of x minus f of a over x minus a. We also discussed this in section 2, that we can also write it as limit as h approaches 0 of f of a plus h minus f of a over h, if this limit exists, basically. And so, and then that's a big if, right? And so if and you notice here that we replace x by a plus h, and then if I replace x by a plus h, and it's a plus h approaching a, so h has to approach 0, basically. So this is telling you that the derivative at each point, you have to recalculate it, basically. So it could be a different value. And so, for example, the derivative of f of x equal to x squared, if you use this limit at point x equal to -1, is going to be -2, and then I can write the tangent line using the point -1 and 1. And that would be -2 times x plus 1 plus 1. So again, the derivative is the slope of the tangent line, and I have the point on the graph. How do I have that 1? X equal to -1, you plug it into here and you get 1. And so another point like 2 and 4, if I plug in 2 in the x squared in the original, I get 0.4, and so 2 and 4 is on the graph. Now, if I take the derivative of the original at 0.2, and I end up with a number 4, and then so I can write the tangent line at that point also. That's 4 times x minus 2 plus 4. So derivatives are different on different points. Yeah, sometimes derivatives can be same, but in general, you're assuming that derivatives are different and you're finding them separately. And the other thing is that you see that basically every point goes to one derivative. And so the derivative becomes a function. And that's a little bit of spoiler of section 3.2. So let's compare the average rate of change with instantaneous rate of change and see the differences. So let y be an f of x be, let y equal to f of x be a function and y equal to s of t be a function of time, t representing the distance traveled from a point. Average rate of change over interval a and b is given by f of average rate equal to f of b minus f of a over b minus a. And slope of the secant line is the same thing. It's the average rate of change. And average velocity is the s at b minus s at a over b minus a, when you have s is the distance traveled from a point. Now, let's compare that to instantaneous rate of change at a. So the rate of change is the derivative, and it's equal, and it's f prime of a equal to limit as b approaches a of f of b minus f of a over b minus a. So it's limits of the average rate of change. It's going to be equal to slope of the tangent line, and the instantaneous velocity, or v of a, is equal to derivative of s prime of a, equal to limit as t approaches a of s of t minus s of a over t minus a. Please notice that tangent line can fail to exist. If the derivative of f of x exists at x equal to a, then f is said to be differentiable at x equal to a. Example 1, instantaneous velocity. For the first 10 seconds after liftoff, the height of a model rocket in meters is given by the function h of t equal to t squared plus t, where t is the number of seconds after liftoff. How fast is the rocket traveling 4 seconds after liftoff? So we're trying to find the derivative of h because we're trying to find the instantaneous velocity, and h of t gives you the distance. And so let's set up, what was the formula? H prime of a equal to limit as t approaches a of h of t minus h of a over t minus a. Please notice that a in here is that 4 seconds. How fast? At 4 seconds. That's the input that we're finding the derivative at. So now set it up by plugging in 4 in this formula. So h of t is t squared plus t, h of 4 is 20, and the denominator is t minus 4, limit as t approaches 4. Numerator factors into t minus 4 times t plus 5, and therefore it simplifies, so I can write it as limit of t plus 5 as t approaches 4. That is exactly 9. Now, what does this mean? It means that the graph of h of t equal to t squared plus t has a tangent line with a slope of 9 at point 4, and what was the h of 4? Was 20 at point 4 and 20. And so I can write the tangent line with 9 is the slope coming from the derivative, x minus 4, 4 is the x value of the point, plus 20, 20 is the y value of the point. That's the slope-intercept form. Example 2, instantaneous rate of change. So what we talked about is basically the definition of the derivative now at this point, and we talked about the instantaneous velocity, but what does it mean, instantaneous rate of change in general? And so this is the question. A manufacturer produces bolts of fabric with a fixed width. The total cost of producing X yards of this fabric is C equal to F of X dollars. Now, what are the units of the derivative F prime of A? So, if you remember, when you're computing the derivative, you're taking the limit of the average rate of change with respect to whatever the input variable is. Here the input variable is X is in yards, the output variable is in dollars. So it would be dollars per yard. Now the next question. In practical terms, what does it mean to say that F prime of 1000 is 9? What is F prime? F prime is the limit when the basically limit of the average rate of change. So let's say this is explaining that if when the production is 1000 yards, the instantaneous rate of change is 9. Or we can say that basically if you increase the production by 1, approximately $9 more will cost you. Now, so the next part is asking, which do you think is greatest? F prime of 5, F prime of 500, or F prime of 5000? So if you notice, according to the second part, one way of explaining this basically F prime at 5, F prime at 500 is how the price is changing if you produce one more yard. And the total cost is changing, and every time you add one more yard, you just add the cost of the material for that one more yard. Therefore all three of them are the same.